distributed storage and research. I'd like to acknowledge the funders of our project, the NSF and Schmidt Futures. For those who may not know much about the Open Storage Network, it's a distributed storage network that currently runs between many of the nation's advanced computing centers. In addition to these sites shown that all have what we call OSN pods, the Pittsburgh Supercomputing Center is another key partner, as well as TAC, where we have one of our advisory board members and hosted our last workshop. We've all come together to try and come up with a platform that provides for ease of deployment and standardized and scalable administration. It's built around Internet 2, currently 100 gig links with 40 gig at one site. This project grew out of a pilot conceived by Alex Szalay at Johns Hopkins University, who noticed that every medium and large research project with large scale data was having to figure out the exact same problem and unnecessarily redirecting time from the research that they had come to do in the first place. We've spent the past year bringing the best of the Open Storage Network findings and lessons learned to the community through a series of webinars and concept papers. We knew that this last webinar needed to focus on the future, and our team felt that the most important thing that we could do today was not just invite thoughtful speakers who all have clear visions, but also to have open debate on the questions that vex all of us. Following this workshop, we will lift up important points raised through today's talks and discussion and publish it in a last concept paper on our website. And this link at the bottom is where you can find all of the previous recordings and our first two concept papers. The webinar just before this one gave a wonderful recap of everything you want to know about the Open Storage Network, technically, as well as who's using it. Today, I'm very excited to welcome people who need no introduction and who are giants in cyber infrastructure. Each will give a short talk, and then we will have 20 minutes or so for panel discussion. We marked an hour and 15 minutes, knowing that an hour would not be quite enough, so I hope you can stay with us. We will do our best to take a few questions at the end, time permitting. As always, feel free to put your questions in the Q&A tool. Our OSN team includes many leaders in research cyber infrastructure who will do their best to answer your questions and flag them for live discussion. First up is Dr. Alex Szalay. His story is one that is common, especially around HPC centers, that he needed cyber infrastructure to evolve for his science and became deeply involved in developing it, despite coming from physics. Alex is PI of the Open Storage Network, and for those of you who didn't know, aside from all these very impressive awards and honors, and really go read his Wikipedia page, he was a professional musician for a time and is an all-around just very nice human. So with that, Alex, I'll turn it over to you.
Thank you. So let me share the screen. So I would like to talk about kind of the sociological background of what is going on today in science, because I think in a sense, these are the major science drivers for what we are trying to do with the OSN and beyond. So traditionally, the US science has been largely bimodal. So there was a whole lot of small PI projects and then a small number of very large kind of $1 billion plus projects like LHC, LIGO, the IceCube, OOI, and you name it. So these were typically driven by the National Science Board. And today there is a trend that is dramatically changing the landscape. It is quite different today. There is much more happening in the middle. So it started out with some of the NASA MIDEXs, the NIH UO1s, and some of the private collaborations and public-private partnerships like the SDSS project in astronomy, but there are many similar projects now. And the NSF also grew out of the NSF MRI program. They actually grew out a mid-scale research infrastructure program. And the typical example of this, or the pattern that is emerging, is to create a unique instrument. This may be a special telescope or a converted existing telescope to a survey project, buy a large electron microscope, buy a lot of genomic sequencers, for example, essentially use cutting edge technology. So create a collaboration around this instrument. So push the technology to the max, take a lot of risks, push the budgets to the limit and sometimes beyond to maximize the science. And this is quite different from the way, the small PI projects can't get anywhere near this in ambition. And the big science projects, because of their nature, they are micromanaged by OMB and essentially have to be very risk adverse, just like a space project where the technology needs to be frozen a decade in advance. And another result of these mid-scale projects and the emergence is that typically the PI is somebody relatively young in the mid-career. It involves a multi-institutional collaboration because of the scale of it, but it is not a too large collaboration. And there is an enormous fresh intellectual energy liberated. So everybody is very driven to actually get the maximum science out. And I think this represents now the sweet spot for science. In a sense, this is where the most important new discoveries are coming out. And this also provides probably the best value for the community for the dollar, because they are putting their data out in the open. So these instruments are not generating a data that will go into a black hole, even though that one of the most interesting projects is about black holes. One of the good examples is the Event Horizon Telescope. The other characteristic is that because they try to be so maximally efficient about the science, they do try to do computations on a shoestring, so they can't afford to build a whole computational infrastructure and environment like LHC can do. So generally, the computations will be done opportunistically. And this means that there is typically the instruments are computerized, so they are generating a lot of data. This is limited simply by Moore's law. So every year they are generating more data, and this data needs to flow from the instruments to large computing facilities. So we see this new emerging computing model where it doesn't matter where computations are done. So basically, the people try to transfer the data where they can get free computer time to process it. So the open storage network emerged kind of at the beginning of this trend, and realizing that science needs a robust infrastructure, cyber infrastructure with three pillars: having computational capabilities, having fast networking to move the data, and we also need a data-intensive infrastructure. And the NSF invested a lot of money in the first two, but really the last was pretty balkanized. And there is a serious impedance mismatch. We may have the fast supercomputers, we have the fast networks, but if I wanted to do a storage layer, this to this transfer from here or from NERSC to Hopkins, it basically went on a 100 gigabit link. It went at 10 gigabit links because the computers on both sides were quite misconfigured. So the idea was that Christine already outlined, that build basically an inexpensive standard appliance that we can just plug into the internet to closets at the universities which have such a high interconnect. And have an open software stack which is standardized, centrally managed, and built on microservices. So try to do the core services that is needed to move data from A to B. And use an ultra simple industry standard API, and we landed on using the S3 object store and plug it essentially into the internet to backbone in the DMZ. And we have right now 8 nodes deployed with extensive testing, and the system is functional and is in use. And so we see now that the OSN can solve the impedance mismatch problem on the continental scale. So it's basically we can move data from the East Coast to the West Coast essentially at wire speed. And this can be actually a petabyte. What are the main trade-offs? This is what I learned when Stu Feldman gave a talk at Szalay many years ago that had really a major influence on my thinking, that computing, extreme computing is about trade-offs. What are our trade-offs? Cost. So the base cost is the price of the hard drives. We have to buy enough hard drives to get basically the speed, and we can't have too much of a multiplier. What is the I/O performance? We have to basically be able to push data out at 100 gigabits. And we need a capacity in excess of a petabyte, otherwise we are not serious. So everything else should be secondary. And the other important thing is that do not try to solve everything for everybody. Try to do one thing, but do that very well. However, we recently started to realize that everybody knows about the last mile problem, but there is also a first meter problem when you build a big instrument. So you build a high throughput instrument where, so say if there is a TEM, a transmission electron microscope, and generally people are trying to tinker with it to increase the data rate, and the trend is now that they are setting up an FPGA rack that does the first stage of data capture and processing at data rates which are terabytes a minute. What do we do with this data? This needs to make it somewhere into a storage, and then it needs to find its way to computing. And it emerges that many people I talk to are looking at the OS and pods as a possible solution, essentially scaling out, and the FPGAs can talk at 100 gigs. So essentially stripe a whole bunch of OS and nodes locally next to the microscope. This cache the data, and then this can be actually then sent on a 100 gig sustain rate to wherever it needs to go. So this can be beautifully solved with dedicated OSN pods acting as high capacity caches. The software is standard and everything is fine. But we need also then do a conversion from the output of the FPGAs onto S3, and so basically deal with the data formats. And this goes against running a fully standardized software stack. Or does it really? And there is another impedance matching here at the 1 meter scale. So the storage part of that story can be actually resolved with using multiple OSS stacks. But how do we provide impedance matching between the custom instruments and the software interfaces of the OSN pods? Basically keep the same idea, but add another abstraction layer on top. So basically run standard software that can run basically secure container singularity, and this can be managed through Kubernetes. And the customization is implemented inside the site container. So we retain the best of both worlds. We provide flexibility, but a controlled flexibility. And what is the trade-off for the experiments? Because this is a very specific environment. So basically the trade-off is that the experiments who decide to go this way, they have to live with the standardization and have to use the customization at the interface and container layer. But it is much cheaper and faster than any other alternative. And there is yet another mismatch on the HPC end. So basically the cheap computing exists in many colors. There are university HPC centers, the supercomputers, there is the open science grid, and there are the commercial clouds. And the computations will be done on one of those. And there's a great diversity in the environments, which puts a challenge on people who want to flexibly and opportunistically jump from one to another wherever they can basically scrunch some free time. And having this containerized interface layer is an elegant solution for this as well. So if we also place OSN pods near the main compute resources in the country, then we can have really the best of all worlds and have a seamless flow of data. So I would like to thank, so this was kind of the vision where I'm very excited how basically this emergence of mid-scale science is really transforming the way we do computing. And all these ideas were really chiseled by a lot of discussions, criticisms, kind of fights with the whole OSN team, in particular, Christine, John, and Kenton. I think I gained a lot from exchanging ideas with Valerio, Michaela, and Jack. And I can't thank enough Christine Borgman and Stu Feldman, again, who really deeply influenced my thinking about how new ideas proliferate and also the importance of trade-offs. Thank you.
Thanks so much, Alex. That was great. And while we're giving shout outs to people, I think we want to give a quick shout out to Al Suarez, our program officer at the NSF, who gave us the additional funding to do this webinar series. Okay, now I'd like to introduce Dr. Ian Foster, someone who needs no introduction. If you somehow don't know him, go look at his Wikipedia page also. You may know him from his work as a founder of Globus, as a founder of grid computing, or because he wrote the book on cloud, which is pretty great, by the way. Globus is an important partner of ours and is one of the ways that researchers can access the open storage network. Ian, thank you so much for taking the time today to be part of this and for all your partnership and integrating Globus with the OSN. And I will let you share your slides.
Thank you very much, Christine. Thanks for having me. Can you see the slides at the moment?
We can, but they're not in presenter view, which is okay if that's easier.
Well, they're supposed to be, but let me just try briefly. I know we don't have too much time. Let's see. Let's try that one. Is that better?
It's definitely better. It's not in presenter mode, but I think
Does it say services for science?
Yes,
Yeah.
we can see that slide.
Okay. Well, given time, maybe I'll just move ahead anyway.
Sure.
So thanks very much for having me on this panel. So I didn't coordinate with Alex, but I think my comments are quite aligned with his, especially my first slide, where I'll point out, you know, I and my colleagues involved in Globus are also very aware of the cyber infrastructure or e-infrastructure challenges that people working in science today face, which I'd say, along with Alex, sort of fall into distinct categories. The small science team, the individual lab, faces, as we have heard, this need for much more computing and data, but they lack the resources and expertise needed to acquire and operate this technology. And then big science, well, projects are mostly busy building out their own vertically integrated stacks that perhaps you know, work well, but are expensive and they tend not to operate. So are there new approaches that we can take to delivering cyber infrastructure? And you know, I believe, argue that indeed there are. And the core idea here is to use a combination of these wonderful, almost magical commercial cloud services that have emerged over the last 10 years to automate much of the mundane and time-consuming activities that underpin science, so that those activities can be performed more easily. Yeah.
So sorry, but we're still looking at the title slide, and we think you probably have meant to move on to the two additional ones. But no problem if not.
It's embarrassing. Yeah.
No, don't. This is, I think, the theme of the last year, and we're all seeing the shortcomings of PowerPoint and Zoom, and so it's definitely not you. But we, everyone was excited.
Yes, indeed.
To see the visual that went with what you were saying.
Oh, yes, and I'd be excited to show it too. Let me try again. I'm going to, who can, let's see. How does that look? Any different? Are you seeing a second slide now? Sharing is paused. Bring your shared window to the front. I don't know.
The window we're seeing, Ian, is your PowerPoint that has the thumbnails on the left. So I think the right thing to do at this point is just click on the thumbnails to advance.
Okay, thank you. Thanks. I'm glad I had a technical expert here. How's that? Does that look any better?
Now we've got the first of that.
Yeah.
Are you seeing a second slide now?
Yeah.
Yes.
Okay, well, I just talked about that slide. Now we're on this slide. Okay. Use cloud services to automate routine and time-consuming activities. So use the power of the cloud to automate while integrating in those resources that we've heard about from Alex, you know, the science facilities, the supercomputing centers, and so forth, which are so essential to scientific progress. So the question is, what services do we need to put in place to allow science to proceed? And we've in Globus have identified some and chose to focus on those. I'm sure there are also others, but let me say a few words about the things that we've identified as important. So frictionless data movement, make it trivial to move data at high speeds, over the fastest available networks, among not only computing centers and personal centers and scientific instruments, but also public cloud storage and other resources. Make it trivial to share data in a frictionless manner with other researchers. And these things may sound trivial, but of course, as we all know, they're not trivial. They are very friction-full in many cases, but we found that we can make them frictionless. And then finally, another thing we've heard about also from Alex is capturing, automating the data pipelines that take data, prepare it for subsequent use, index it, analyze it, reduce it, and so forth. So we could go on, but those are three things that get in the way of science, and we could accelerate by leveraging commercial cloud services in conjunction with the resources that we have available. And that's what we've been doing with Globus over the last 10 years, basically, providing cloud-hosted services for identity management, workflow automation, file transfer, file sharing that engage and interact with storage systems and scientific instruments across the research and education ecosystem. So what makes it possible for us to build these services? Well, first of all, we leverage powerful commercial cloud services. We happen to work with Amazon, which we find works very well, but of course there are other providers who also provide beautiful technologies. And the fact that you can, for example, use a cloud service to replicate some indexing or transfer management capability replicated across multiple availability zones to provide very high availability, that you can use state management and queuing services to provide high availability, high performance workflow management. These are all things that are just fantastic, and we couldn't possibly do if we tried to do them ourselves inside our university or lab data systems. But at the same time, the data itself that we're working with, and the computing that we're often working with, is located within scientific facilities. So we need well-connected scientific facilities, which we have increasingly, thanks to very high-speed networks, data transfer nodes, science DMZs that have been deployed increasingly in most, maybe even almost all labs and universities across the US. And then sort of drilling down a little bit, one thing that we find incredibly useful in the science projects we work with is to have storage that can be accessed programmatically, sometimes as an impedance matching capability, as Alex indicated, between a science instrument and a high performance computing center, sometimes for more long-term storage. And we've had really good experiences with a couple of such Globus enabled storage systems. At Argonne, we have the Petrel data system, which is now scaling up to 50 petabytes, which is being used for a tremendous variety of activities, some relating to scientific instruments, some to simulation. Basically, it's a device that you can put data into, pull data out of using Globus mechanisms without having to know anything about how it operates. And then the open storage network that we're starting to work with in the same mode. Online storage, Globus accessible, a wonderful impedance matching capability, and in some cases also a long-term storage capability. So we need this online storage to enable the applications that increasingly scientists are building. What makes them usable is cloud-hosted science services. We've developed a number of them in Globus, but I'm sure that there are others that are needed. And we should be thinking hard about what aspects of our science workflows we can outsource to cloud-hosted services. I think that's a very important thing to be thinking about that can potentially transform the way people interact with scientific data and scientific facilities in general. So thank you very much, Christine.
Thank you so much, Ian. And there was just a quick question from the audience. Zach Byerly asked what impedance matching meant in the context that you were discussing and on that last slide.
So what was the question again? Sorry. Oh, here it is, Q&A.
Oh, yes. So just a quick.
Oh, yes, I'm sorry. Yes, so impedance matching. What is impedance matching? Yep. Right, so this is probably a term from electrical engineering, but yeah, the idea is when you've got say an instrument producing data at very high speeds, you eventually want to process it on several remote computers, but you need somewhere just to send the data immediately, so it can flow immediately into a large storage system online without you having to, spend weeks finding a storage system to which you have permission to move data, and then it can then flow on to other places as required.
Perfect. Thanks so much, Ian. And we will have a little more time at the very end for additional Q&A, and we'll do our best to be answering these in the chat as we go. Okay. Next up is Dr. Ed Lazowska, a computer scientist who has played a very important role in the research of our field, as well as in the establishment of services for researchers, especially for me, that has impacted my life greatly. His pivotal role in establishing the eScience Institute, more recent initiatives like Cloud Bank, and I've been proud to partner with him for the last 5 years on the West Big Data Innovation Hub. Another person to check out his Wikipedia page. He's received every honor I can think of. And for those of you who don't know him personally, he has a fantastic sense of humor. And if I could give an award for the best talk title and abstract of the year, Ed would get it for the one that he gave us for this talk. It's on our website. Thank you so much for being willing to take part of this and for giving it to us straight with no chaser, Ed.
Great, hang on a second. Let me try and make my screen sharing work. The same problem everyone has had.
I hope it won't work for you as well, so that
yeah, I'm counting on it not working.
I don't look so.
Actually, a version of screen sharing is not working, so hang on a sec. Okay, how's that?
Perfect.
Great. So I'm being deliberately provocative, and I want to be clear that that's the intent here. I go back years and decades in some cases with Alex and Ian and Christine. So let me just continue in the provocative theme here. This is a song I've been singing for a long time, and that is that science should make greater use of the commercial cloud. And so this dovetails very nicely into Ian's presentation. This is a slide from a talk I gave to the Computer Science and Telecommunications Board back in 2016, plea for greater attention to data-intensive discovery and greater use of the commercial cloud. And I began this talk with a slide of Yogi Berra saying it's deja vu all over again, because I had given the same talk previously. For example, I gave it to CSTB previously in 2014. And I gave it to the National Science Board in 2013. And what I pointed out is that we have this dogged resistance to utilizing commercial software services and systems in our field and in universities. We purchase our own, we operate our own, we roll our own, often with amateurs. And in many cases, it's because of outmoded policies, subsidies, turf defense, politics, people whose paychecks depend on running computers, and failure to do a hard-nosed cost-benefit analysis. And all of these things plague businesses as well as universities, except businesses sometimes have fewer hidden subsidies than we have in universities. So I obviously don't have to go through the litany of attributes of the commercial cloud, huge capacity, you pay for what you use, no capital cost, extraordinary burst capacity, operations support, reliability. While you just sit there, it gets bigger, faster, and less expensive, which is very different than what you capitalize. The software stack is diverse and high quality. I'll talk a bit more in a minute about proprietary hardware and software and the integration of the stack, but I think that's important going forward, and we're trying to look for the future here. A much better environmental footprint, I'll say something about that. Obviously, easy sharing and collaboration, Ian spoke to that. Enhances reproducibility, configuration choices evolve, purchase models evolve, competition is growing for research business. Okay? So let me talk about proprietary hardware, software, and the co-design. The commercial clouds are now moving beyond Intel and NVIDIA, which have, in some sense, inflated prices. We can buy a different class of NVIDIA GPU to stick under our desk than Amazon is able to buy, but they will not be buying GPUs from NVIDIA much longer, nor will they be buying processors from Intel, I suspect. And I think going in the future, private clouds are going to be doomed to inferior hardware, software, integration, and cost performance, because you won't be able to buy for yourself what Amazon and Microsoft and Google and IBM can provide in an integrated way in which they're designing their entire stack from the hardware on up. Environmental footprint. Google's power usage effectiveness is dramatically better than the average. Some of their data centers use 90% renewable energy, much better than our academic data centers. Obviously, major companies are choosing the commercial cloud. And one thing I'll mention is several years ago, Andy Jassy, when he was running AWS, gave a talk here at the University of Washington. And he mentioned that 5 years previously, AWS would approach Fortune 100 companies and they would never get beyond the CIO, and the CIO would listen politely for 20 minutes and then would dismiss the AWS folks and go back to doing what he or she had always been doing. And what was happening 5 years later was that CEOs were calling AWS and asking to come visit. And when they visited, the CIO was not in the room. And the reason was that boards and CEOs over those 5 years had figured out that the CIO had sold them a bill of goods. I can do it less expensively. I can do it more securely, on and on and on. And there's just no reason that that's the case. Why can we do this less expensively than Amazon or Microsoft or Google or IBM? So there are a set of issues to resolve. And as we go forward, in terms of cost, there is plenty of headroom between what it costs the commercial cloud providers to vend the service and what they can get away with charging for it. And I think that's really important. We have to deal with persistence of the stack, right? We're never going to be, research is not going to be a big enough proportion of their business that that we cause capabilities to persist if they are no longer valuable to other aspects of their business. So that's something we have to deal with. Various forms of widely used software, even open source software, becomes rigid. There's a socio-technical and governance issue here. And we have to provide multi-cloud support for mobility, and CloudBank is beginning to become a model for that. Here's some approaches to cost reduction. One is let nature take its course. As the cloud providers increasingly move to proprietary hardware and a proprietary stack, their costs will decrease, okay, and their prices as well. Secondly, negotiate. As I said before, there's a gigantic gap between what they charge and what it costs them, okay? Google, for example, has a great margin on preemptible TPU cycles for which it charges only 30% as much as cloud TPU cycles. So, an example that I could imagine is that researchers pay the cost and the providers make a philanthropic contribution of the difference between the cost and the list price and take a tax deduction for their philanthropy. Okay, so I think there's room for negotiation here if the research community bands together and does it. Harder but interesting, and this was proposed to me by Bill Hilf at Vulcan, legislation could require that a commercial cloud provider selling to federal accounts provide equivalent or some relevant ratio of highly discounted capacity to US nonprofit research institutions. Okay? So there are things we could do to negotiate improved prices and data egress and things like that. So in summary, 2 words, commercial cloud. And as I said in my abstract, we should be negotiating with commercial cloud providers for acceptable terms rather than building our own private cloud. I think the path we're pursuing is one that's not going to be an appropriate path in the long term. That's my provocative commentary. Thanks for listening.
Thanks so much, Ed. And, you know, so many times in science, we forget that everything that came before us came through discussion and vigorous discussion. And so that's exactly what we were hoping to have today. And thank you so much for delivering. So last but not least, I'd like to welcome Dr. Ryan Abernathey to give us a perspective on how he has used the Open Storage Network on his Pangeo project that is at the forefront, bringing cutting-edge technologies together to serve the geosciences. Like so many of us, Ryan is incredibly busy, but never too busy to give up his time, and he has been a key partner on so many projects, including EarthCube, where our team has worked with him to establish notebooks as a new form of scholarship, along with papers, presentations, and posters. Ryan's accomplishments are also numerous, but I will just turn it over to him. And thank you so much, Ryan, for joining us.
Okay, you see my slide?
Yes, we do.
Okay, great. Well, thanks a lot for the invitation. These slides are online if anyone wants to go through them later in the link provided. Let me get right into it. So most of what I'm going to say today is in a paper that we recently published in Computing and Science Engineering. And I want to acknowledge all the co-authors here on that page, and also want to acknowledge NSF EarthCube project for supporting our work. So let me just introduce Pangeo in one slide. Pangeo is a sort of a grassroots community collaboration between environmental scientists and software developers that sort of emerged from the scientific Python world, open source scientific Python world, focused on developing tools, improving infrastructure around big data processing, visualization, and machine learning. In environmental sciences, like in almost every scientific field, we now have a flood of data. You know, we measure our data sets in petabytes, and that really led to some major challenges in terms of our tool set. So the Pangeo community came together to try and sort of upgrade our technology stack so that we could take on bigger scientific challenges. Within Pangeo, we've been thinking a lot about how we work with data. What are the access modes? I and most scientists, I feel like we grew up on this idea of the download model. The way you get data is you download it, and then you bring it onto your computer, and that's how you work with it. And what we've realized is that this is actually a huge barrier, not only to sort of efficiency, but a lot of other things that we care about, like reproducibility, collaboration, and inclusion, because you bake in this dependency on sort of your local file system into everything that you're doing, and it becomes very hard to share a data-driven project in that context. So what we'd like to do instead is move to what I call a cloud-native model, where instead we're bringing our computing close to the data. So Pangeo currently operates a lot of cloud-based infrastructure in all major commercial cloud providers, Microsoft, Amazon, Google. And we have a pretty strict separation between the data side of this and the compute side. On the compute side, we're heavy users of the Jupyter based ecosystem that includes Jupyter Hub, Binder, that are really great tools for interactive computing and reproducibility in the cloud. And on the data side, we've been innovating around cloud optimized formats like ZAR, which are really designed to work with object storage. And we've recently been looking at Open Storage Network as an alternative to using Amazon S3 or Google Cloud Storage as a place to put our data. And I'm going to just demonstrate that in a second. So, going back to commercial cloud storage, one of the biggest projects that we've been involved with is bringing a new public data set to Google Cloud and AWS, which is the Climate Model Intercomparison Project, over a petabyte of climate model prediction data that's now available directly from object storage. And is really having a huge impact on the way scientists are working with climate data, and also industry and other sort of non-scientific actors who want access to that data. So we're very excited about this sort of thing. I'm going to quickly demonstrate the software stack that we're using to interface with cloud computing and object storage. At the base is a storage library called ZAR that is optimized for storing multidimensional arrays in object storage. We use a parallel computing framework called Dask. And on top of that, we use Xarray, which is a high-level API for analysis of multidimensional labeled array data, which fits is a description that fits a large fraction of scientific data. So to demonstrate what this is like, I'm going to open a data set directly from OSN right now, live in this slideshow, just to drive home the reproducibility aspect of this. So I've just pointed this at an OSN URL. And what I can see is I can look at a bunch of different arrays within this data set. I can examine their size and structure. So here we see a chunked multidimensional array, about 4 gigabytes, stored in 100 megabyte chunks, each of which is an individual object in OSN. And the cool thing here I want to drive home is I opened up this massive data set in one line of code. No file downloads, no parsing massive, lists of files. This is just one data set. And now I'll make a little interactive visualization of this data set on the fly. And we'll explore it just to illustrate the reproducibility. So the data set here is a sea surface temperature in the Gulf Stream. So this is New Jersey up here, and we can browse through here, zoom in, jump to a different time step, and it's pulling the data all live, no downloads, just computing directly on OSN. So that's pretty cool. I'm going to move a little bit faster. I'll just note that we can also, using the same technology, use distributed computing. So say if we wanted to take the mean of a big data set, we can use distributed processing to do that. I'm not using any distributed processing here, but I'm still going to, take the mean of this, multi-gigabyte data set just directly over the internet in a few seconds. And if I would use a big compute cluster, I could do that all a lot faster. So the last slide before I wrap up here, what we did is to evaluate OSN. We compared the OSN throughput to Google Cloud Storage, doing our computing right in Google Cloud. And we found out, somewhat surprisingly, that for modest levels of concurrent reads, say like 50 simultaneous reads, OSN is actually faster than Google Cloud Storage. And we're typically getting read throughputs of, say, 5 gigabytes per second. And this whole thing, whether you're using the cloud or OSN or whatever, it's nearly 2 orders of magnitude faster than sort of a legacy data portal that's common in our field. So I want to agree with Ed's general point. I'm a big fan of cloud computing, and particularly on the compute side, between the TPUs and all of the fancy, automated things, it's impossible to beat what they have, except perhaps for data storage. So commercial cloud object storage is very expensive. And you pay, unlike the burst capacity that you have for computing, that's not the way data works. If you want to maintain a data archive, you have to keep paying for it every minute that it's there. I've also noticed by working on this for the past few years, scientists have an existential fear of losing control of their data to the cloud providers. There's some really, many scientists deeply want to own the hardware that their data sit on for very profound, psychological reasons. And that may be a hard thing to overcome. So there are alternative storage providers like Wasabi, coming in around 50K per petabyte year. OSN, assuming a 5-year lifespan for the pod, is about 30K per petabyte year. And as I just showed, it works almost just as well as Google Cloud Storage, at least for our use case. So obviously this, I really like OSN as a sort of solution to the hybrid, in this sort of hybrid cloud world where we're using cloud computing, but perhaps storing our data outside of the commercial cloud on OSN. A huge issue, though, for if we want to pursue this approach will be egress. There's going to be high volume of traffic. We have to find a way to bypass those egress costs if we're going to go this route. We have to, co-locate the pods, work with the cloud providers, make sure we are not getting charged egress for compute access between OSN and commercial cloud. Otherwise, that could kill this approach. We have to obviously sort out the governance, who owns the OSN pods, who allocates the storage. The software stack will need to change if we're going to move to this way of working. Most workflows are still based around file-based data analysis, and so object storage works very differently. Perhaps the Pangeo stack can be helpful here. And finally, we need to figure out how to stage our data to OSN. Often it's much more than just copying files from one place to another. We actually have to transform the data to make it compatible with object storage. The Pangeo Forge project has been thinking a lot about this. And I'm sure I'm out of time, so I'll just put up my last slide about Pangeo Forge, which is the exact sort of service that Ian referred to. We're trying to build a service that will make it easier to transform data from legacy formats into cloud optimized formats and store it in object storage providers like S3 or OSN. So sorry for going long. I'll stop there.
No apology needed. That was great. Thanks so much. Okay, now with the time remaining, I'd like to pose a few questions to the panelists, just some quick bookkeeping. I'll call on you individually for questions that I think connect with your talks, but I do want to invite each of you, if you feel strongly, to speak up and comment, but don't feel like each of you has to answer every question. And to our listeners, thank you for engaging us with the Q&A tool. Our team is doing our best to answer your questions, or at least give thoughtful responses. And if there's time, we will lift up a few of those for live answering. Okay, so in no particular order, Ian, I hope you don't mind if I put you on the spot first, but I'd just like to ask you a real open-ended question. What trends do you foresee over the next 5 to 10 years in research, e-infrastructure, or cyber infrastructure?
Oh, wow, that's a nice general question. So, well, just off the top of my head, what we're seeing is in the work we're doing is, increasing use of being made of so-called AI, machine learning technologies, and therefore a whole new take on what sort of infrastructure we need for science. In terms of the computing platforms that are available to us. Second, increasing people pushing computing towards data sources in order to do effective data reduction and feature detection where data is being produced. I think because data volumes are growing, we're going to see increasing importance of community data sources. It becomes harder and harder to justify people making personal copies. So I think the work that we heard about in the Pangeo project is something that we should be seeing more of in many different disciplines. And then, as I've said before, I think we're going to, I hope, see people working out how to combine commercial cloud with its many benefits with the science infrastructure that we already have or that we are creating in a way that democratizes access to powerful resources.
Thanks so much, Ian. Just a quick invite, but no pressure if anyone of our speakers wants to add on and lift up something that they see as important for where things are going.
Well, can I maybe show a quick slide? Because
Please.
So being in the music world for a while, so it's interesting to see how the music industry has evolved. We used to buy LPs and CDs, took it home, then came iTunes, where I can download. I don't have to buy the whole LP if I want to listen to a song, but from iTunes I can grab a single song. And today we are actually streaming it from the cloud. And how do we do science, data science? We basically download all the data and take it home and play it on our own computer. That's the CD equivalent. And the database servers are the iTunes model, where I download the data one song at the time. And what is happening unavoidably that it will be in the cloud. And we don't even know what the file formats are, but we will kind of see the stream of the results. And we are right now somewhere in a transition place. But it's unavoidable that in 10 years, most of our stuff will be in the cloud. So I agree with that in the long-term future, but basically having to serve a lot of free data for free, and I'm not getting any money from the NSF for it. So I have to figure out the most economic way to keep the astronomy data alive for its legacy. And so I have to do whatever is the cheapest today. And I know that where my threshold would be that I would be happy to jump over to the cloud with the storage. So, and
Alex, sorry. Maybe that's a good segue to ask you. So in regard to commercial cloud and shared research computing resource
I think
in the last few years.
I think you froze in the middle of the sentence. Your Zoom froze.
Okay.
Yeah, if you could.
Oh, of course. Well, I guess this goes with all of the other theme of everything we've seen over the last year. Thank you, Home Internet. But Alex, I just wanted to ask you, how has your thinking changed in the last few years in regard to commercial cloud and shared infrastructure?
Well, no, I always saw, that clouds are inevitable, but the pace on which I think compute is already cheaper with AI. Today, I think it's time not to buy any more GPUs because the GPUs get outdated in a year. If I buy something on a university budget, the expectation that it amortizes in 5 years. So it's much cheaper at this point to actually rent the GPUs, so things with a fast turnaround and fast amortization. But I agree what Ryan, I have to underline what Ryan said, that storage today is still not the right way. I think the reason for the egress fees is that we have to use commercial networks to download the data, and the cloud providers want to get reimbursed for it. So if we could actually ensure that we have private fibers going into the major cloud data centers, that may be a good starting point for the negotiation of a better rate. And for the long-term data, I can also see that if we know that the data is going to be there for 20 years, the cloud providers know how the storage prices are going to drop over 20 years, so they can take it into account already in today's prices. So I can see a lot of place for negotiations there, but they don't solve the first meter problem. Capturing the data at the instrument, this will be always our task, and to make sure that it somehow gets into the cloud. So that's the future-proof model of computing, I think.
Thanks so much. Ryan, you're someone who is very adept with using commercial cloud and of course using all sorts of different types of infrastructure. Do you have any comments to make about the differences between using something like OSN and then commercial cloud, just from the user's perspective?
Well, I think it was a very wise decision to adopt a standard API, the S3 API for OSN. The worst thing for interoperability is when people decide they need a new standard, a new API, a new protocol. And so, because OSN picked the S3 API, we were able to just completely move our whole storage stack almost trivially into OSN. There aren't, right now with OSN, there aren't any, at least I'm not aware of any like higher level services. Like there's no website I can use to browse the files. Like there's no front end, let's say. And that would certainly be useful. Alex mentioned, the possibility of deploying, compute stuff and near the pods. And I think, there to some degree, that's a slippery slope, as Ed suggested, but for instruments and stuff, it will be unavoidable. There still needs to be hardware, sitting next to a microscope or a telescope. And in that case, continuing to use standards like Kubernetes is key. And finally, I would just really want to plug the open source stack for interoperability, right? The cloud providers are always trying to one-up one another by building new features that are exclusive to their cloud. And if we want to maintain a competitive environment, we need to instead commoditize the cloud computing so that they're all essentially providing the same thing and just competing on the performance. And so I think open source tools have a key role to play there in avoiding sort of technological lock-in to one cloud provider.
Maybe Ed can just go talk to the different commercial cloud providers for us and bring that message back and just get it fixed.
But let me correct one thing. So maybe it didn't come through well enough, but in a sense, the idea about putting a thin computational layer on top of OSN is to run things like PangeoForge. So basically format conversions, but not to run the juicy computing. That's not the job, but actually do the trivial task that you would have to do on your own machines otherwise. Instead, you load basically the PangeoForge container and you just pump your data in one format and it goes into S3 right away. So that's the idea. So
in terms of just a comment about, Ryan's good point about a high-level interface or interfaces. One or Globus is one that can be used for that purpose, for browsing, transferring, accessing the metadata, searching for content. I'm sure there could be others as well.
Thanks so much, Ian. So Ed, actually, I'd like to take a question that came from Andrew Bingham, if you're willing. He asks, commercial cloud has the advantages you describe, but touching on Ryan's thoughts there, what are your thoughts on vendor lock-in and long-term data preservation, right? If the vendor gets out of that business overnight.
Yeah, I think these are really serious issues. And it's a conversation I had with a set of Alex's astronomy friends at one of our national data science meetings a couple of years ago, Andy Connolly and others. And I think the issue of lock-in, I think, is addressed by utilizing multiple vendors. And clearly you have to have your foot in multiple camps or you're held hostage. So that's an issue. I think the issue of data persistence can be dealt with. The issue of application persistence is something that I worry more about. And that's equally true for open source software. Okay, so you could imagine that anytime somebody builds a science stack on top of open source software, there should be a plan, a commitment for the preservation of that stack, because we often have the need to go back and recompute across data and repeat experiments, and we can't afford to have the software stack go away. So again, I think this is a problem that affects even our own open source work, not just the commercial cloud. But in the commercial cloud, they clearly are going to be responsive to their greatest customer base. And even though research computing is, I think, clearly billions of dollars a year, that's a small fraction of the current income of the commercial cloud vendors. So there would have to be some negotiation here. And again, I think the critical thing is for us to band together and work with the government and try and do that negotiation, because several $billion is still a pretty good business and a worthwhile business. And as someone pointed out in the Q&A earlier, this is also a way for the vendors to get generations of students hooked on what they're selling, right? And I mentioned in response to that question, this is it didn't have a particularly happy ending, but this is what IBM was doing in the 1960s when they were heavily discounting physical mainframes to universities, right? We all benefited enormously from that back then, and their goal was less, let's say it was enlightened self-interest. But I think that Amazon and Microsoft and Google may well have the same enlightened self-interest. So I think there's room for pressure here.
And just to pick up on a theme I also saw in a few questions, I know CloudBank is presently only for a few communities with who are funded by NSF. But perhaps you could say just a little bit more about what you see as the need of organizations like CloudBank to simplify that accounting interface to the commercial cloud vendors for science.
Sure. So I think let me give just a bit of background on CloudBank first. This was a National Science Foundation project. It's an award to UCSD and Berkeley and the University of Washington to build essentially an interface to all of the major commercial clouds, initially for size researchers in response to specific solicitations. And I'll get back to that in a second. But it does, through a third party, handle issues like billing, runaway instance control, and things like that. So there are a lot of services that that we need in academia, because we're often dealing with, every year it's another set of new users, right? And so unfortunately, the same mistakes get made, and the vendors have not had the sorts of controls that we need for that audience. So we're trying to provide those. When Jim Caroso was the NSF Assistant Director for SAIS, he tried to get the Office of Advanced Computing to do a solicitation like Cloud Bank for the entire foundation. And they were not willing to take that on. So Caroso realized that he was able to do that for SAIS researchers, that is, researchers in his division, on his own initiative. But the expectation was always that this would grow. And indeed, other directorates, particularly the geosciences, but others, have expressed a keen interest in utilizing Cloud Bank as an interface. And also the good folks at UCSD have a service called Cloud Bank Enterprise, which provides essentially similar services for anybody at universities, not just enterprise computing, but research computing and educational computing. So I think there's an expectation that this will grow. People are surely aware of this thing that's called variously the National AI Cloud or the National Research Cloud. There's a serious impetus to build a cloud for research, which I certainly hope, while it may have a modest private cloud component, and clearly for certain types of research, you need to have a cloud under your control, in particular for research on cloud technologies. I certainly expect that this national cloud, if funded and off the ground, and there's a 12-person, 16-person working group now that's being constituted to come up with a plan for this. So it's a serious initiative. I certainly hope that what it will do is use multiple commercial clouds as the principal back end. My fear is that the folks who like running computers will try and turn this into a national scale private cloud for science. And that's really the road to ruin that I speak of.
But I think if I can add to this, I fully agree. But so this is why I felt it was so important what Ryan was telling us, that essentially the scientists cannot just keep doing the same thing. They also have to adapt towards newer technologies, which makes it much easier to dynamically switch from A-type computing to B-type computing to C-type computing. So to make our user codes more portable, which means probably going away from POSIX and going into you getting used to storing our data in object stores and so on, and containerize all our computing, etc. And I think it will be worth it. So, but this is why I talk a lot to Chris Boardman, who is into technology adaptation, etc. So what makes people tick and when they want to switch technologies, and what can we do to facilitate these processes?
Yeah, perfect.
So
Ryan's example of using the right API was
and if everybody did that, then our life also, as the trust, we still have to be, there has to be a layer of trusted intermediaries between the, like in publishing, this was the traditional publishers, which are being replaced by the archive and the open source journals. But there still has to be, again, an impedance matching between the computational world and the scientists who make this transition and adaptation a little bit easier. So. And I think this is the role of many of the people who are in on the seminar, I think, and also in the audience.
So I just want to lift up a point there that you raised, Alex, and that we made an important decision to go with object storage, and it wasn't always popular. And we have had that argument over and over. And I think this is a point of convergence where I'm hearing, even though it seems like a simple thing that many of us take for granted, that things are moving away from POSIX to an object store type cloud model. Anything more you'd like to say? Because I think there's a large swath, especially of the research computing community, who think that's not true. too uncomfortable a question.
Yeah, that's why we need to do so. Okay, so there will always be people who want to run on Lustre, and Lustre is certainly more appropriate, at least currently, for most of. Okay, so today we build the supercomputers to run the 70s Fortran codes still. Okay, all right, and so that basically determines the operating system model that we want to use. Once we are going away from this, and maybe on the exascale, we will have actual neuromorphic layers in the hardware, etc. There will be a lot more flash or non-volatile memory on each of the nodes. So the architecture will be so different that we'll have to rewrite the applications anyway. And I think Ian is quite involved with that process. So maybe that would be the time to switch.
So, and Alex, maybe just to lift up another point. So how do we protect against the obsolescence of OSN? Because I think we've seen great demand for it, which we showed on our last webinar, different use cases. And also, by the way, for those of you who didn't see the last webinar, we do talk about integration with commercial cloud and use of caching and things.
Yeah. So I think the first meter issue is critical for the future of OSN. We will always need the first meter solution, but I think the OSN will shift its focus. So today, actually, the biggest need is in storing the petabytes of user data somewhere and make it in a way easy to send anywhere. I think in 10 years it will shift. It will be more act as a caching layer, which provides a low latency near the pods and basically otherwise enables the data again to move freely. But the data on the OSN will be just probably transient. So it will move through the OSN, but essentially it will become a caching layer, which we will still need. And I will see more OSN kind of do the Akamai thing, so and migrate it into the network hubs. And like Starlight, so that some critical data can be actually posted there that at a lower latency to everyone.
I'd just like to give a moment for any of the speakers to comment on anything we've discussed so far. Maybe you have a last thought that you felt didn't get raised or you wanted to put a finer point on it. Please feel free to say so. Well, we've had a very active, oh, please, Ryan, go ahead.
Well, I would just say, I feel like to some degree, the HPC community feels a little bit missing from this conversation, right? Because, that's a huge source of data is coming from the HPC centers, as in the form of simulations and stuff. So right now we have this workflow where, we essentially are bringing data out of HPC centers into the cloud to make it more accessible. But, I'm sure they have their own vision and view of, what they should be doing. And I would like to hear from those HPC people about how they see OSN fitting into their plans.
Sure. I don't know that I could carry that load, but I can say that the OSN is basically housed at HPC centers. And so it's but go ahead, Alex.
Yeah, but I think there will be also a dramatic shift in the way the supercomputers will generate the simulations, because it can't go on. It's incrementally. So basically imagine that we have a computer that is 100 times larger. Okay, so we want to increase the dynamic resolution of the partial differential equations. We need to pack in more cells. Because of the cells, we need to decrease the time step. The lapse time of these simulations is still going to be the same. Or if not, if it won't get worse, even though our computer is 100 times faster, then the traditional model has been that we were generating a bunch of snapshots, which are horizontal cuts in the data. At the equal time slices, we just dump everything that is in memory. Why are we doing the simulations? Because we are interested in the highly nonlinear phenomena, which are very localized in a tiny fraction of the volume. Most of the rest of the simulation is very boring laminar flow, which could be easily interpolated in a much lower resolution. So we will have to figure out a very different resolution or very different representation. Maybe the neuromorphic layers in the supercomputers are going to find these nonlinear patterns and we store them as objects in an object store as a localized event. So it will be more event-driven than snapshot-driven representation of the data. And then we will have otherwise kind of the boring part of the simulation will be just kind of compressed in a lossy fashion. So, but we will have to rethink entirely how I think the simulations are done. So, because
there's a lot of exciting work being done.
Yeah, well, yeah, absolutely. So
a lot of exciting work being done in areas like, is it neural network acceleration of simulations? Neural network or AI, so-called selection of the next simulation to perform. It's fascinating.
Yeah. So it will be a whole different ballgame in no matter what. So.
Just to add a quick thought as an HPC Center person, many of us, and I think I speak not just for the San Diego Supercomputer Center, but our peers, we see ourselves as advanced computing centers. Some of us even have names that say that instead of supercomputing. And the data intensive computing that's become, part of the conversation and taking over how we're doing it. Of course, big iron's important to us, but we see ourselves as places that bring the facilities that don't exist, and we keep innovating. And as things commodify, we move on to the facilities of the future, wherever those are, in the cloud or in our data centers. So any last thoughts? No, Ryan had something he wanted to lift up. I see a few thought bubbles. It's okay if you want to keep them to yourself, though, if you're just enjoying the conversation. Well, I do want to invite the people watching today and the people that are watching later, the recording, to check out our website. We have some new and updated information on where the project is. I'd like to just share a couple email addresses. If you have a burning question, if you're trying to figure out how to put a pod into a proposal, you'd like to create a virtual pod, you want to figure out how to get an exceed allocation, you can't go wrong contacting Julie Ma or myself. Here are our email addresses. Our website is theopenstoragenetwork.org. We thank you so much for being with us today. And I really want to thank our speakers. They're all great friends and colleagues. And I know I really enjoyed the conversation, and I'm sure that our everyone watching did as well. So I'll close now, and thank you again so much.
Thank you very much. So.